Welcome back. Today we're going to continue our discussion of systems with conformal symmetry. In the past couple of lectures, we've discussed what the words conformal symmetry mean. And this led to the introduction of a group, a mathematical group, which we'll call conf R, P, Q, the connected component containing the identity of all conformal diffeomorphisms of the pseudo-Riemannian manifold RPQ. So that's the symmetry group that we call the conformal group. That's what we've seen in the previous lectures. We also discussed infinitesimal conformal transformations. And that led to a algebra called the Witt algebra in 1 plus 1 or 2, 0 dimensions. Of course, we also discussed infinitesimal conformal transformations in other examples of P and Q, but there the algebra is much smaller. Only here in 1 plus 1 or 2 plus 0 dimensions is the algebra bigger. And bigger is better because it means you have more symmetries, you have more conserved quantities, and you can eliminate more degrees of freedom. So you may potentially be able to solve systems which have a large number of symmetries. So that's the story so far. This is just introducing the terminology, introducing the things that will allow us to define a conformally invariant theory. So this is what we begin today. So a conformal theory, at its most basic, gives some kind of representation of these groups on the degrees of freedom of the theory. So I won't say what the word theory means quite yet. So let's call this conformal theory version 1. A theory which has a representation of this group, or carries or furnishes a representation of this group here. And in fact, before I continue, let me point out something about the symmetry group here. The symmetry group here contains time translations inside it, by definition. It has time translations. It has spatial translations. It has boosts. It has dilations. And it has special conformal transformations. This we've seen so far, right? We've been through all of that. So that means if you have a theory with a representation of this group of symmetries, that representation already has a Hamiltonian built into it. Generally speaking, the generator of time translations has a name. We call it the Hamiltonian, both in classical and quantum theory. Now, I've been very vague about what theory means here. For now, just think of it as some kind of theory which gives me either probabilistic or deterministic results when I make measurements. And this here is a kind of working definition of what it could mean to have a conformal theory, something with a representation. And it's important to note that in contrast to other symmetries, and I've made this point before in the various quantum field theory courses, in contrast to, say, non-relativistic settings, if you want a theory to have a bunch of symmetries, in a non-relativistic case, you would just demand that the symmetries commute with the generator of time translations. That's sort of the usual scenario in non-relativistic physics. However, relativistic physics, which is what we have here, because we have boosts in that group, that's no longer the case. For a theory to be relativistically invariant, you can't demand that H commutes with all the other translations, rotations, boosts, and so on, because boosts mix energy and momentum. So boosts will intertwine, well, intertwine is not quite the right word, it'll conjugate spatial translations to time translations. So you have to do it all at once. You can't do it like in the non-relativistic case where you build your non-relativistic theory and then you sort of focus on invariant sectors to get the rest of the symmetries to work. Here you can't even get a theory with a Hamiltonian independently of dealing with all these other symmetries. So you have to represent them all at once in these kind of theories, both Poincare invariant theories and in conformal theories, which are a superset of symmetries. Now maybe this isn't so hard. It could be that it's easy to find representations of the conformal group. And the answer is, well, yes, it is pretty easy. We can characterize them. We have this thing called Lie group theory, Lie algebra theory, work out all the representations. But we're not by any means done if we do that, because those representations that we write down may not look local in any sense. Really, we want something more. And that something more is locality. And what locality means here, to be somewhat more precise, is that we have a list of observables or a collection of observables let's give them a name, let's call them phi. This is what we're going to use for the rest of the course anyway. Phi, these are just observables in your theory. This could be a classical theory, in which case these observables will be functions on phase space. Or it could be a quantum theory, in which case these observables are presumably self-adjoint operators. Or it could be a generalized probabilistic theory, where these phi's are some element of some ordered unit vector space. So we don't have to be specific about the theory when we say what a theory means to be local. We have a collection of observables labeled by two, or at least one thing, but possibly two things, labeled by points in the manifold itself. Now that's not because we have this notion in looking around us that physics is local, that, you know, I can do something here, you can do something over there, there is a here, there is a there. We have a notion of independence between different locations in space and time. So that means we want our observables to be labeled by an element of the space-time. Now, when you characterize representations of groups, you don't always get such observables. You get, you know, perhaps if you do unitary representations, you get a Hilbert space handed to you, and you get a matrix, and that matrix is the one that does time translation, that does spatial translation, and so on. But you don't get handed a list of observables. You get a Hilbert space and a unitary matrix when you do unitary representations. And similarly in other representations, non-unitary ones, same thing. A representation of a group of symmetries is just a map, pi, from your group of symmetries to some set of matrices. So a finite dimensional representation looks like that. An infinite dimensional representation might take you to the bounded operators on some Hilbert space. It might take you to the linear self-adjoint operators on a Hilbert space, blah, 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 blah. Every possible infinite dimensional version of the word matrix you can think of, you can build something called a representation. So representations do this, but this doesn't hand you that necessarily. So we can completely characterize the irreducible representations of these groups, Poincare group, Lorentz group, rotation group. We know all the irreducible representations, conformal groups no exception. But finding theories where you have a collection of observables labeled by space-time is harder. And it's harder because this is a reducible representation. So it's likely, I mean, it's not, I'm not going to prove this, but it's likely that a representation of G which has or furnishes a collection of local observables is reducible. So it's going to be a direct sum of irreducible representations, and possibly a very complicated direct sum indeed. Now you can often list all the irreducible representations for a group. They often form a discrete series, sometimes a continuous series. And you feel as though the job's done once you've listed all the series. Because that's it, you know, every irreducible representation has to be one of these representatives in this series of representations. However, if you're worried about reducible representations, then there's no limit to the evilness that can occur, right? Because a reducible representation is one that's a direct sum of irreducibles, and there's an infinite number of ways you can build these things. So there's tension. Where's the tension? The tension's between irreducible representations, which are a tractable beast, and locality. Now, sometimes it is the case that you have local theories that also are irreducible representations, or give irreducible. That happens, right? But they don't happen to capture all the physics that we know and love. So we're forced to work with reducible representations. This has a lot to do with many particle quantum theory representations of the Lorentz group. So to play this game, it's not enough just to say use representation theory. We have to do something more. We have to impose these assumptions in a different way. The assumption that our theory is local and gives rise to a representation. So what we're going to do is promote locality to the most important thing now, and then look for ways that a local theory is conformally invariant, rather than looking for ways of sticking together irreducible representations to give us local theories. That's somehow the more complicated direction. Doesn't mean it's impossible, it just means more complicated. And to that end, I mean, we're not so much interested in this course in classical theories. The emphasis here will be on quantum conformal theories. But a lot of the terminology and a lot of what we know about quantum conformal field theories is motivated by what you observe for classical field theories. And so we come to the topic of classical field representations of conformal symmetry. The reasons I say field here, fields are the only kind of general purpose way that we know to furnish a local set of observables. Well, why? Because they are pretty much, per definition, a local collection of observables. So the locality question is sort of done when you consider field theory. Now we have to ask the question, you know, what constraints does conformal symmetry put on a classical field theory? So just recall Let's recall how to do symmetries in classical field theory. This is something we covered at the beginning of the first quantum field theory course. But it doesn't hurt just to remind you and set some notation here. So a theory here is now a highly restricted definition. In classical field theory, not only in classical field theory, the word theory is much more constrained in its definition than the one I gave up there, because we make a huge number of additional assumptions when we say we have a classical field theory. So a classical field theory is colloquially, traditionally, something is specified by an action. You don't have to specify it by an action. This is just a way of compactifying, compressing the equations of motion. That's a very convenient way to do it. And an action is an integral of a Lagrange density. So we've already made a massive number of assumptions here. We've assumed that the equations of motion are represented by the action, which is an integral over space-time of a Lagrange density. The Lagrange density itself is taken to only depend on the fields and the first derivatives of the fields, but nothing higher. So we've made an enormous number of simplifications in that, in writing just that line there. Even there, that's still a lot of field theories. But we've thrown out, with this line, all non-local theories. We've even thrown out theories with dependence on second-order derivatives. So just a warning there. And phi underline means you've got a bunch of fields labeled by some index set. And this index set here is meant to represent the different field types in your theory, different particle types in your theory. Or vector quantities such as the electric field, or the vector potential, or tensor quantities. A is meant to cover all of that stuff. This index here, A, runs from whatever, 0 to infinity, and every label in that list is meant to capture the degrees of freedom in your theory. Now, what does it mean for a classical field theory to be symmetric or invariant under a symmetry transformation? Well, we have to do the symmetry transformation. So we know how to do it. Right? When we have the labels that comes from the manifold RPQ, then we actually know how to do our symmetry transformations. I'll write them abstractly to begin with. Other way around. So you do a symmetry transformation, you take one location and you map it to its image under the symmetry transformation. That's how you do it, right? What happens to the fields under these transformations here? Well, it depends if you take a passive or an active view of doing this transformation. In the active view, you take the field at location X, you apply the symmetry transformation, which means you actively do something. You push the field, you rotate the field to a new location. And in the process, the field is now located or moved to a new location, x prime. But also, under the transformation, the field itself can be transformed. So that's what a symmetry transformation looks like. I'll draw a picture. Suppose we have our space-time is two-dimensional and we have a vector field, a field that's everywhere, a two-dimensional vector. And I'm going to show you the result of, I draw a picture of an active rotation of our space-time. All right, so here's like a picture example, just to get you used to the terminology. So we're going to just look at Euclidean space. And we have a field on Euclidean space. What is that? We're going to have a vector field. Let's take a two-dimensional vector field all over space-time. Could have had 3D. We could have had a tensor field. I just happened to choose a 2D vector field. So maybe you think of this as the magnetic field, right? At every point in this space-time, there's a two-dimensional vector, which I'm indicating as a little arrow. So our field is just a map from R2 to, in this case, R2, right? Because it's a two-dimensional vector everywhere. And then if we do an active transformation, an active rotation in this case, say by some orthogonal matrix O, which is cos theta sine theta minus sine theta cos theta, then what we end up with, well, you can just sort of, let's focus on the vector, the field at this point x here, before the rotation. So here's x. What happens to x? Well, it gets rotated, right? By some angle, theta. So this vector that was pointing sort of in that direction, after this active rotation, you imagine that you took your system and you turned it around. That's the active version. Then this point has now moved to this point, x prime, and the field vector, this two-dimensional vector, gets rotated as well. There's a non-trivial action of our rotation on that vector field. So it gets rotated around. And the same goes for every single point in our space-time, right? Every other point there's a vector, it gets rotated. Now that's if we have a non-trivial action of the rotation group on this vector. We could have had a trivial representation of this vector, of the rotations on this vector, where we just don't rotate the vector. We move the fields, but the vectors stay always pointing in the same direction as before. That's a trivial representation. Here's a non-trivial representation, just to distinguish between those two. So after you've done your transformation at the point x, what's at the point x now? Well, not the field, but the field that was somewhere else, right? The field that was over here to begin with. It gets moved to x. Maybe it's pointing like that. So the field that was, that is now at x after the active transformation came from a location O inverse x to begin with. O inverse x gets mapped to x. So the result of this active transformation gives you a new field which has some non-trivial dependence on the previous field configuration. I'll leave that there for a second. Think about that picture. So the field that is now at x after the transformation is equal to the field that was at O inverse x, plus some additional, perhaps additional stuff happening on the index A. So I'm going to write that out. I know this is elementary, but there is a tendency to be a bit blurry about whether your transformations are passive or active, and then it can be very confusing in the future. So let's just specify things in the active viewpoint for now. So after the symmetry transformation, the new field configuration at X, because there's going to be some new field configuration, but you're allowed to put in the argument X. Well, the prime indicates that it's new. What's it equal to? Well, it's equal to the field configuration at O inverse X plus some possibly non-trivial action on the field components B. So you take your field configuration, you do some active transformation on it, now you have a new field configuration. Let's ask, how does the action of this new field configuration, how is it related to the old one? Well, S prime equals, you just do it. I'm going to write out the answer. It's an exercise, it's one you've done before. I'll just write the answer out. Okay. Oops, absolute value. So we have a Jacobian, right? You change variables, so you're going to get a Jacobian. That's what the Jacobian looks like. I've left the dependence of this new field, phi prime x, just written as a calligraphic F that sort of captures all the spatial bits and all the bits that act on the vector labels. And then, because you also have a first derivative in here, you're going to have some dependence on the first derivative as well. So that's what a transformation does to an action. And we say our theory is invariant or symmetric, or is a conformal field theory if it leaves the equations of motion invariant, not the action. The action doesn't have to be invariant. Just the equations of motion. And what that means is that the action is allowed to change by a total derivative. Sorry, the Lagrange density is allowed to change by a total derivative. Of something. So I've better give that another name, right? F is taken, L is M. And then we discuss things like Noether's theorem and so on. But that's what we mean, invariant theory. Now let's see what that means in terms of the field operators. We'll be able to learn how field operators transform under conformal symmetries by just analyzing representations of our infinitesimal generators of the conformal group. There's no particular surprises coming up, but it's just worth going through this carefully because we're going to introduce some new terminology to do with spin and so on. So what I'm going to do next is see this transformation law here. We're going to investigate this transformation law for the bigger group of conformal transformations. I just did it here for two-dimensional rotations where things are straightforward because we know all the representations of the rotation group. They're labeled by integers. But the conformal group might have some new elements. It turns out it doesn't really, but still, let's do this properly. I guess I will, discuss the rotation group case a little bit more just so you're not surprised by what comes up. So for the rotation group here, we have more or less sort of two kinds of fields that you can end up with. So we have trivial fields. These are ones where this pi of O is just the number 1, or in fact it's just a delta function. So that's a representation of the rotation group. Every rotation is represented by the number 1. Obviously 1 times 1 is 1, so it's a representation. And this is the one where the vectors don't rotate, so to speak. We have another representation called the fundamental representation. That's the one that I've written down there. And that's just the one where pi of O, A, B is really just O, A, B. Just take out the matrix element of the rotation. These are real representations here. If we have complex representations, then everything's trivial. Right? Because every rotation is it's an abelian group, it's going to be a phase. Now, if you think about other groups, say the three-dimensional rotation group, there the representations are a little bit more non-trivial. We have some irreducible representations. So I'll just write in one line the three-dimensional case. So the three-dimensional rotation group, suppose we have a rotation invariant theory. What kind of representations does this give us? Well, it gives irreducible representations labeled by spin. Right? I won't even put quote marks around it. That's standard terminology, which is a half integer, yeah? 0, 1 half, 1, 3 halves, blah, 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 blah. So the kind of theories that you get, the kind of symmetric theories, will depend on a spin label. So this matrix here will be, in the three-dimensional rotation case, be one of either the zero spin case, the half spin case, and so on. And then you can work out this matrix, and that matrix turns out to be a 2j minus 1 dimensional, 2j plus 1 dimensional matrix. Yeah, 2j plus 1 dimensional matrix, yeah. So it's a one-dimensional matrix in the spin 0 case, it's a 2 by 2 matrix in the spin half case, it's called the spinor representation. And in the spin 1 case, it's a 3 by 3 matrix, which just happens to equal the fundamental representation, and so on, blah, 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 blah. And so therefore you see that your fields, your sort of irreducible fields, the ones that you can't build from other fields, will be labeled by spin. Now in the conformal group case, it's just the same, basically, because the conformal group contains the rotation group, so you know that that's going to appear somewhere. And it sort of intertwines with boosts and so on, but there's no, I mean, there are some subtleties to do with boosts, which we'll sort of completely ignore, and just end up concluding that our irreducible representations will again be labeled by spin. No point in making our life more complicated if we don't use the complicated stuff later. And the way we're going to do our study is not in terms of the group itself, but the Lie algebra. It's just simpler to think about infinitesimal rotations than it is to think about rotations. And we're going to do it in arbitrary dimensions to begin with, because this is where the terminology comes from, and that's what I want to introduce today, the terminology we use to talk about representations of the conformal group. So we're going to think about infinitesimal generators. Just recall we've got names for them. So the infinitesimal generator of translations is momentum, called P mu. The infinitesimal generator of dilation is called D for dilation, and it's given by that minus I x mu d mu. We have two more we have to deal with, rotations, which include boosts. There's D choose 2 of these. D choose 2. No. We don't have L00, we don't have L11. D minus 1 over 2. D choose 2. Okay. In any event, those, when they're non-trivial. And there's one final class of transformations that we've encountered called special conformal transformations. That's when you invert through the origin, do a translation, and then invert through the origin again. K mu they're called, and they have this form here, which we basically encountered last time. Okay, that's the infinitesimal generators of the conformal group. That's the number 2. That's the vector x squared. So every conformal transformation is a product of one of these, and infinitesimal ones are going to be commutators of these. Now, in almost any high energy theory book that you ever pick up, you'll see things like this written out, and then you'll see long lists of commutation relations. There's no avoiding this. This is essential if we want to work with these things infinitesimally. So here we go. Here comes the long list. So these are the generators of all these infinitesimal transformations. But what, oh what, that looks like when I do one then the other. Well, we have to work out commutators. So you get a Lie algebra. And yeah, you sit down, you work it out, and you get a long list. And this long list carries a lot of information in it that's very useful. So let's start with the long list. What happens if you do a dilation, then a translation, and vice versa? Well, you get something new, and what you get is I times p mu. This is just an exercise. I don't know a quick way to do this or to remember this stuff. What about dilations and special conformal transformations? Well, you get that. It's an exercise for the reader. Well, yeah, we don't stop here. There's more to come. I mean, when you write down this many generators, you know you're going to have about 16 things that you have to worry about. Well, obviously 4 of them are trivial, things that these guys commuting with themselves, although not here. Even here, life is complicated. So, yeah, I don't know a magic trick to remember this stuff. So you just have to write it out. Special conformal, and of course it gets 10 times worse when you consider supersymmetry, where you enhance your symmetries with fermionic symmetries, and then these lists sort of fill pages. It's just life, I'm afraid. So eta is the metric. I believe at the first lecture I already said that I'll be jumping between eta and g's. So that's how special conformal transformations and translations relate to each other. Then we have to worry about special conformal transformations and boosts and rotations. So far it's sort of manageable. I mean, I hope it's sort of clear how to get each of these commutation relations. You just stick in this and this, for example, apply the derivative operator to these x's, you get some delta functions, blah, blah, blah. What about translations and boosts and rotations? This is an interesting one. This is what makes it all so difficult for us. That's a row. And you can see a lot of physics in these things here. Right? You know, this says what happens if I do a boost. What happens to the energy momentum 4 vector? Well, it gets rotated, right? That's what this stuff is doing here. Rotates energy into momentum and things like this. So there's physical content to these that you can sort of begin to see if you think about what each of these commutators represents. And the last one, the ugliest one of all, although is what happens if you do 2 boosts, or rotations, then life is going to be complicated. There's no denying it. And it's got to do with the phenomenon of the fact that a rotation and a rotation isn't the same as just a simple rotation. You have to worry about how vectors rotate on the celestial sphere, and also 2 boosts can give you a rotation. That's a Thomas precession effect. Yeah.
Sorry, it is right that in the commutation relation between K and L, that there is a P.
That's a row.
No.
Oh, on the other side that there's a P. Oh, hang on, maybe I miswrote that. K and this one here, yeah.
Yeah.
Right. Thank you. Yeah, that would be weird. I hope that's correct now. Yeah, this is almost, if you know that a special conformal transformation is basically a translation, but where you've inverted through the origin twice, then you know that it would have to be some kind of special conformal transformation after a boost or a rotation. So here, boosts and boosts, yeah, it's going to be complicated because of Thomas precession. If you boost once in one axis, boost along another axis, that's equivalent to a boost and a rotation. So, yeah. When nothing commutes, all bets are off. Okay, I think that's correct. There you go, I managed to get it all on one board. Which one commute, sorry? D and L commute. Yes. If it's not there, they commute. Yeah.
In the last line, on the first two terms, there are two rows.
Oh gosh, yeah, there is a mistake. Okay, there's a mistake with what's written. Mu nu minus mu nu. That looks okay.
No, in the second term of the last line.
Oh, yeah. There's two mistakes, right? Nu rho, rho sigma. Wait on. Okay, that doesn't work at all. Oh, mu sigma. Gosh, thank you. That's my handwriting. And here there's mu sigma. Mu sigma. Nu rho. Okay, that works. My mu's look horribly like rhos, unfortunately. All right, so we want to understand what kinds of quantities can transform non-trivially under this collection of things. So this is our task for today. So we want to find out what kinds of fields transform, give representations of the conformal group and how. So this task is greatly simplified by the fact that I'm going to assume you know the representations of the Lorentz group. So the Lorentz group is a sub, or the Lorentz, the Lie algebra, the Lorentz group, the Poincaré algebra, is a sub-algebra here, right? You just have to, ignore D, the dilations, and ignore the special conformal transformations. And you see that you're left with this subalgebra, just this one here, P's and L's. And if you know, you should have been exposed to, and you should be willing to go and look for the classification of the representations of this Lie algebra here, and you'll see that they're labeled by spin or helicity, depending on whether your particles are massive or massless. I've mentioned this in quantum field theory before. So in fact, our only goal for today, our goal is very much more humble than completely understanding all the representations. All we want to understand is how does K and D act on a pre-existing representation. We're going to use hopefully we'll have still representations of the Poincare algebra. Well, we do, right? We must have, if we have a representation of this conformal stuff, then by restriction, we automatically have a representation of the Poincare algebra. You just don't do special conformal transformations, you don't do dilations. So we know that whatever representations we have will be labeled by spin or helicity. And then our only task is to understand how does D act and how does K act. And that's it. That's our goal, and we'll be able to achieve that goal relatively rapidly by using a trick. So we already know if we have a field that transforms in a non-trivial way under the conformal group, then it transforms under the Poincare group. Simple statement. If we have a field that under a general conformal transformation, so here's our field with its label x, suppose it goes to pi of some lambda a b phi lambda inverse x b then by restricting only to Poincare transformations, we know that this gives a representation of the Poincare group here. Possibly reducible, right? It might be to get a representation of the conformal group, you need to take the direct sum of a bunch of representations of the Poincare group. They might get mixed together by these additional transformation rules here. Now our task today will be to find out how does D and K act. And they'll turn out to act really simply, so there's no real, things are pretty nice. And the way we're going to do it is we're going to study a subgroup of conformal transformations, namely the ones that leave the origin fixed. you can think of translation. I mean, translations are a bit of a distraction, right? They move the origin. They don't act in any other way other than to move your field at some space-time location to another. No particular rotations occur along the way unless it's in a magnetic field, in which case then, or a gauge field, then you have to worry about parallel transport, but we're not going to go down that road. We're going to think about just fields which transform in the obvious way under translations. So translations are a bit of a distraction in this story. All the non-trivial stuff in this transformation law over here is really that, right? It's this additional rotation that a vector field might experience when you do the rotation, or the boost, or the dilation. And to isolate out that non-trivial dependence, we focus on the focus on the subgroup of conformal transformations which leave the origin fixed. So the field before at the origin is the field at the origin afterwards. I hope you can already guess what that subgroup looks like. What transformations have that property? Well, boosts and rotations do, right? In one frame, something's at the origin, then in the new frame after a boost it's still at the origin. I mean, everything else gets squished and rotated, but something at the origin remains at the origin. Dilations also leave the origin fixed, and so do special conformal transformations. So these three things are left, they fix the origin. This is a subgroup. And we can look at the infinitesimal generators, and we'll see that they form a subalgebra. Because any composition of these things forms a subgroup, so the generators will form a subalgebra. Right. Okay, yeah. So e to the I omega A generator A. Probably a bad notation. Let's stick with alphas. So suppose you have an infinitesimal conformal transformation that is some combination of boosts, dilations, and special conformal transformations. So omega A is infinitesimal. We want to think of a little one of these. How does the field transform now at the origin? So the origin, phi at the origin, goes to, well, pi of this, right? Origin. This is the nice bit about this assumption. So by composing these transformations one after the other, blah, 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 you'll see that these matrices, these are just matrices now, will form to close a representation themselves.
You can focus on the subgroup that leaves the origin fixed because it just don't care about translations.
So the question is, why am I focusing on the subgroup here? The answer is we want to understand D and K. We know how P and L act in general because I've assumed that you know how representations of the Poincare group look like. The only thing we haven't really dealt with is D and K. Now D and K are in that subgroup that fix the origin. So why even complicate our lives if we can throw out the translations? Now, you might say, well, why don't we just focus on dilations and special conformal transformations and leave the rotations away? But you can't, right? Because if you do a boost and then a dilation and a special conformal transformation, they commute. No, right, because we want to use information we have already, namely that the boosts give a representation. Sorry, that we have a representation of boosts, we understand what they look like. Then what happens if we add in D's in terms of these things we already know? And we should already get a hint of how things are going to look like because dilations commute with basically everything, right? So I'll give you the answer already. How do dilations act? Well, they act trivially because they commute with boosts. They commute with special conformal transformations. So we learn something very valuable right now, which is dilations never have a non-trivial action here if this is an irreducible representation of the Lorentz group. That's the result I'm going to show in the next minutes. And then furthermore, once you know that the dilations act trivially, you learn that the special conformal transformations act trivially. That's a non-trivial piece of data that comes out. And that comes from these relations up here, as we'll see. Yeah, see this one here? There's D's and L's there. Oops, I realize I've just, no, it's up there, sorry. D's and K's also act non-trivially with each other. All right, let's get to it. So when we do an infinitesimal transformation, we can use Taylor series, and the fact that this thing here is going to be assumed to be continuous, to write that as P of the identity plus I omega A. And so this G of A is a generic term for any one of our generators. Either K mu, D, L mu nu. I think that's it, isn't it? Yep. So we're going to call by pi of D, give that a name delta twiddle. So whatever it does, it's called delta twiddle. We're going to call pi of kappa of K mu, we're going to call that kappa mu, some matrix. And pi of L mu nu, we still need to worry about it, we'll call S mu nu, it's actually the spin representation. What spin does the field have? And the only other thing we have to worry about is, that's it, yeah. So if you now look at what your these matrices have to do, you see that near the origin, they have to obey the algebra up there. These matrices here, which tell us how the field, how this transformation acts infinitesimally close.
Say what delta twiddle is?
I haven't said what it is. I've just given it. This is just a name. I'm just going to call by pi of d delta twiddle, just to make it clear. I mean, I could have left pi's everywhere, but I don't know. Didn't have to. Oh yeah, there is a reason. I mean, notationally, this is what will correspond to something called the scaling dimension of a field. So that's the term, the notation people use. We're stuck with it. So as this is a representation, it must be that it's a representation. So it must be that those matrices here obey the rules that the Lie algebra obeys. And that's actually all I need, I think, for the argument, just these three. So if you do an infinitesimal dilation, a little one, on your field, it leaves the origin fixed, and the way the infinitesimal dilation acts is by this possible non-trivial matrix delta twiddle. Now I'm going to argue that the matrix delta twiddle is actually trivial. And the way it works is, suppose the generators of the Lorentz group, the rotations and so on, are an irreducible representation. With some spin or helicity. So suppose we have, you know, what we want to do is break our fields into things that can't be broken down any further. So suppose that the boosts themselves, these rotation matrices themselves, give us a representation of the Lorentz group, and that's an irreducible representation. You can't break it into a direct sum of any others. Then this equation here, it's a very important equation. It tells us that delta twiddle commutes with every one of these generators here. Now, because this is an irreducible representation, there's something called Schur's lemma. Schur's lemma says that if you have a generator that commutes with all the other generators in an irreducible representation, then your generator here must be trivial. It must be a multiple of the identity. It's Schur's lemma. Go away, prove it. It's an exercise. It's really a simple exercise. An extraordinary result, but a simple exercise to prove. We already learned that delta twiddle is proportional to the identity. So dilations don't act in a crazy way, they act in a very simple way. Now comes the really remarkable consequence. You might be worried about special conformal transformations. They have a good chance of acting non-trivially. Because there's inversions through the unit sphere to the origin. I mean, they might act non-trivially. But look at this. That second commutation relation there tells us that minus I kappa mu is 0. They don't act non-trivially at all. They act as 0. They act trivially on the field labels. They act non-trivially on the spatial labels, but trivially on the field labels. So Schur's lemma immediately tells us that kappa mu is 0. Kappa mu is 0, commutes with 0. It's all good. And then if you go back up to the full Lie algebra here and check, is that all consistent? You'll see that it is, right? If a representation of kappa k is 0, then all these commutation relations where there's k's will vanish on the left-hand side and on the right-hand side. Remember, this is the subgroup at the origin. Now we're going to introduce some very important terminology. This delta twiddle has to be proportional to the identity. How is it proportional to the identity? We're going to give it a name. It's going to be I times delta times capital I. Delta appears throughout conformal field theory, and this is why. This is how the dilations act on scalar fields in classical field theory. So I'll write out that action. So remember, a finite dilation is just a sequence of infinitesimal dilations. I'm going to focus on the spinless case, fields without spin. It's a bit more complicated when there is spin, but turns out that the physics we're going to look at in this course will be spinless fields. So we're looking at x gets mapped to lambda x. That's the full conformal transformation corresponding to dilation. And what we've learned is that if you have a spinless field, or even a spin-full field, that delta twiddle equals I delta times by the identity. So at the origin, the field transforms as at the origin identity plus I delta twiddle epsilon identity plus I delta twiddle many, many, many times. Right? If you want to do a full dilation, you exponentiate yeah. So there's the fundamental result. If you do a scaling transformation, dilation, this is an additional transformation that comes from conformal symmetry, then your field at the origin transforms to some scalar factor times the field at the origin. Dilating by lambda is the same as dilating by a little bit many, many, many times. And that's how you get the lambda in there. So every field has a characteristic behavior under dilations. Delta doesn't depend on anything anymore. It's a number, a fixed number that's attached to the field.
So it has the index A.
Has the index A, for example, which I should have put in there. Thank you. Oopsies. Yes. All right, so every conformal field has a behavior under dilations, and that behavior is called the scaling dimension. Now actually we don't use delta to label scaling dimensions, we use delta. Delta A. This is an additional quantum number that comes into play when you talk about conformal field theories. I said quantum number. I shouldn't have said quantum number, but it will be. We'll promote it to a quantum number in the coming lecture. Yes. Now you might guess this on the basis of physical arguments, but here is a consequence of representation theory. And it's worth expressing that transformation law slightly differently because, well, you'll encounter it when we talk about quasi-primary fields in the next lecture. So it's worth noting that lambda, the scaling factor, can be related to the Jacobian. It's not a very deep statement, right? But if you do a dilation, then the Jacobian equals minus lambda to the minus d over 2, where d is the space-time dimension. And lambda is the scaling factor in the metric. Remember, a conformal transformation leaves the metric invariant up to a scale factor. And you can relate lambda to big lambda to our little lambda like that. The scaling factor for a dilation is little lambda to the minus 2. Under a dilation, the metric gets transformed to the metric, but by little lambda to the minus 2.
You missed something. You want to say transformed.
Thank you. I missed something indeed. Otherwise it's 0. Don't want that. And so there's another way to express this law here in generality, and that's the one that we're going to use for the rest of this course. So that is that the field, now we can add back in the spatial dependence that's a prime here. So under dilations, that's how fields transform. It's an equivalent way of doing it. I mean, I could have just left it at lambda to the minus delta, and we often will, but it is worth having this alternate way of expressing it here with a Jacobian instead.
Does this work for every point in space?
It works for every point in space-time, right? Because we've worked out, I didn't say that, how do we get this to work on other points in space-time? I have 5 minutes. I'll mention briefly how to get this to work on other points in space-time. So to do that, I'll have to remind you of the Baker-Campbell-Hausdorff formula. Well, hopefully you remember the Baker-Campbell-Hausdorff formula. So we know how dilations act on the field at the origin. Now we wonder, how do they act everywhere else? Well, the Baker-Campbell-Hausdorff formula tells us. Or even, I think, I could probably short-circuit that discussion by just simply reminding you how a transformation works on a field, and then you probably will see it straight away. The field at X is equal to the sum over B, the transformation but we now know should have, sorry. We take the representation, and now that's a delta function, delta AB. You might be unhappy with me extending this representation to everywhere, every spatial label like that. Well, another way of getting rid of being more comfortable with this is this Baker-Campbell-Hausdorff argument. I hope that is already fairly convincing as an argument, but to do it completely properly, we have to express it in terms of what happens at the origin. A very quick sketch. A translation is e to the I x rho p x rho p rho. And then we might wonder, how does a translation act on the generator itself? That will allow us to pull out a translation overall up there. And you use the Baker-Campbell-Hausdorff formula right here. To learn that that equals that. So in this way, you can see that the generator D, when acting on phi of x, and that fills in, it's an exercise to fill in the missing step up there. All right, so noting that, yeah, I'll leave it at that. So this is a brief whirlwind summary of classical field conformally invariant field theories. And essentially the whole goal of today's lecture was to argue to you that fields, when you do a dilation, transform in this particular way, at least when they are irreducible representations, coming from irreducible representations of the Lorentz group. And that number there is a very important quantity, the scaling dimension delta, and it'll appear throughout all our quantum treatment. So the quantum treatment is what happens in the next lecture. That's where we say we no longer care about classical field representations, we're looking for unitary representations of this group. So that means we need Hermitian operators or self-adjoint operators corresponding to D's and P's and K's and L's. And then we want to understand those representations. We'll see that they get labeled by quantum numbers, and those quantum numbers will include these deltas here. Also the spin of the fields. The representations will be labeled by spin and delta. And a third quantity called the central charge, which comes about because we need to consider a more general class of representations than just unitary, namely projective unitary representations. So the plan for the rest of the course is, in the next lecture, let's just suppose we magically have a representation. What constraints does that put on the correlation functions of our theory? We'll understand that in the next lecture. Then we'll get into the business of projective versus unitary representations in generality. We'll see the emergence of this thing called the central charge. And then probably, maybe, we'll get to fusion rules in this course. We're not going to get very deep into the theory of conformal field theory here, but we're going to understand the basics well. Okay, but for now, that's it. Thank you.